So I wanted to finish this proof of theorem 410. So as usual, L is a semi-simple complex Lie algebra, and X is an element of L. So we defined this abstract Jordan decomposition. X is D plus N, where D is such that the at D operator is diagonalizable, N is such that the at N operator is nilpotent. And then we fixed any representation of L on a vector space V. And the claim was then the Jordan decomposition of the operator by which X acts on the vector space is given just by the images under the representation map of D and N. So we've been working on that a lot, and I think now we can finish this theorem. So the proof the first step was to do the following. I want to show the Jordan decomposition of this operator is given as follows, but I can consider this operator as an element of the Lie algebra phi of L. And then we showed that, so the image of the phi map, this is still a semi-simple Lie algebra, so this operator also has an abstract Jordan decomposition. And our first step was to show that phi of X equals phi of D plus phi of N is the abstract Jordan decomposition of phi of X. So that means the adjoint operator at phi of X decomposes as at phi of D plus at phi of N. So this is then an honest Jordan decomposition. And so, of course, we have to show these four defining properties. We always need to show when we want to show that some additive decomposition of an operator is a Jordan decomposition. So this was they add up correctly. Well, this is obvious, and they commute. I think this is also obvious. And then the last thing I did last week was at phi of D is diagonalizable. Yeah. So now the last property to check, which we will do now to finish this first step of the proof, is of course to show that at phi of N is nilpotent. Well, let's just check it. So by assumption, here we have the abstract Jordan decomposition of X. So add n is nilpotent. Say now I have to fix some power which vanishes, say, add n to the m is the 0 map. So I want to check whether add phi of n is nilpotent. So I have to apply add phi of n to several times. So this, say we'll just try with the same m. No? In another application we had to double the m here, but let's try to whether the same power will annihilate every vector here. So we want to show that this operator is nilpotent. So this is an operator on phi of L on this Lie algebra. So we have to apply it to test vector phi of y. So for y, an arbitrary element of the Lie algebra, then phi of y is an arbitrary element of phi of L, so of the vector space on which add phi of n acts. And let's just check whether this works out. So what's that? Add phi of n to the, I just split off the rightmost application. So this is add phi of m to the n minus 1. And then I have to apply add phi of n to phi of y. So that's phi of n commuter with phi of y. So I have supposed that phi is a representation. That means a homomorphism of Lie algebras. So I can take the phi out of the bracket. So that will give I just copy the first part, and then I get phi of n y. Right. So I can write this again as add n y with this add notation. So what happened here? Somehow I started with add phi to the n m and applied it to phi to y. And this is equal to the following thing. I just apply this operator add phi of n one time less, but instead I have to put the operator add of n inside and apply this to y. So and I can just iterate this procedure. Now with the next computation I can put the next rightmost application of add phi of n inside. So eventually I get this is phi of add n to the m applied to y. So this is all the same calculation as here. So formally you would use induction to prove this. And yeah, then we assume that this is 0. So this is 0. So we picked an arbitrary test vector here and showed that this operator evaluated on this test vector vanishes. So indeed add phi of n to the m is 0. So at phi of n is nilpotent. So we finished this step here. Yeah, and now to finish the proof, of course, we have to show that phi of x is phi of d plus phi of n is the non-abstract, so the actual Jordan decomposition of phi of x. And for this we use the uniqueness of the Jordan decomposition. Well, let's just introduce some variables. So phi of x is some operator on V, so it certainly has a Jordan decomposition, and I denote the diagonalizable operator now by capital D and the nilpotent operator by capital N. So this is the Jordan decomposition of phi of x. So D and N are just matrices on V. So, right. Linear maps from V to V. And now I use something you did as an exercise on exercise 5.3. There you showed how to compute the Jordan decomposition of at phi of x from the Jordan decomposition of phi of x. Well, or there was no phi around, but the Jordan decomposition of at of something from the Jordan decomposition of something. So in our case, the Jordan decomposition of at phi of x is at d plus at n. So the adjoint operator for d is the diagonalizable part, and the adjoint operator of n is the nilpotent part. So on the other hand, by step 1, we just computed the Jordan decomposition of at phi of x and showed that this is, so let me write it down. Part 1, Jordan decomposition of phi of x, of at phi of x. The abstract Jordan decomposition of phi of x, so this is the actual Jordan decomposition of at phi of x. And we just showed that this is at phi of x is at phi of d plus at phi of n. And so by the let me just finish this here. By the uniqueness of the Jordan decomposition, they coincide. So at d is at phi of d, and at n is at phi of n. And then we showed that for semi-simple Lie algebras, add is injective. This was in one of the proofs. I forgot in which one. D is phi of D, and n is phi of n. And so this finally proves the theorem. So the proof is kind of long, but not too complicated actually. So it's just a two-step process where we want to show this, what I like to call universality property of the abstract Jordan decomposition. So whenever I fix an abstract Jordan decomposition, x equals d plus n, so that means that's what becomes the Jordan decomposition with the adjoint representation. Then that becomes also the Jordan decomposition with an arbitrary representation phi. And somehow the trick here is to apply an extra layer of the adjoint representation. So it's somehow the picture is here we have our Lie algebra, and then in order to define the Jordan decomposition for our element x of the Lie algebra, we have to go to the adjoint representation, and then we can define this abstract Jordan decomposition. And now we take another representation phi, and I want to see what do we get here. Does this also yield a Jordan decomposition? So for some reason we need to apply another level of taking adjoint operators. So this is what we did in step 1 to show that here we get the correct Jordan decomposition, and then by injectiveness of the add map we show that we get the correct Jordan decomposition here. So anyway, this is a very abstract picture. If you don't like it, never mind. But so this is the structure of the proof. Yeah, and this is the end of the chapter 4 about tools for studying semi-simple Lie algebras. And we continue to the next chapter. So what I want to do now is to state the main ideas and give an overview, because as I said in the beginning, I won't be here for 2 weeks now, so I plan to make a bit larger exercise sheet which you can retrieve on Thursday. And so I hope you will have the chance to continue studying this a bit, but I want to make the ideas clear now. So title is Weights and Roots for semi-simple Lie algebras. Yeah, as we didn't work with weights and weight spaces for a while, I just recall briefly the definition. So if L is a Lie algebra and V a G module, sorry, later I'll switch the notation, but an L module so a representation, and lambda is a linear form on the Lie algebra, so homomorphism from vector space homomorphism from L to C. Then we defined the weight space so denoted V lambda. So this is a vector subspace of our representation space V. And namely it was the set of all those vectors which are just scaled when I apply an element of the Lie algebra. And the factor by which they are scaled is just given by applying this linear form lambda to x. This was our definition. But so the observation is we already considered a couple of examples, and this is sometimes this seemed to be useful and sometimes it seemed to be not useful. So this is not always useful. So what do I mean by this? Let's recall some of the examples. So the one was L is the Lie algebra of upper triangular matrices. So fix some n by n matrices, and there should be zeros below the diagonal and arbitrary components on or above the diagonal. And V, the vector representation of this Lie algebra. That means if L consists of n by n matrices, then V is just C to the n, and the Lie algebra acts by matrix vector multiplication. So and I think we thought about weight spaces here. So it turns out there is only one-dimensional non-zero weight space. So the only non-zero weight space is the vector space generated by E1. So why, if I take a vector here which is only a first component non-zero and I do matrix vector multiplication, then I just get a multiple of the same vector. And what's the weight? Well, the scalar by which I multiply such a vector, which is only first component non-zero, this is just this component of the matrix, the upper left corner of the matrix. This is, if you think about how you do the matrix vector multiplication, this is the number by which this vector is stretched. So this is of weight epsilon 1, where epsilon 1, so this is a map from L to C, linear form, and this is just the projection on the upper right, upper left component. Well, so I think we didn't do this, but you can convince yourself that this is the only weight space which occurs here. So if we make the n large, so the size of the matrix is large, then V will be a very large vector space, but the only weight space is one-dimensional. So this doesn't contain very much information probably about this whole representation. So this is one of the cases where this idea doesn't seem to work out too well. We find a weight space, but it's just one weight space, and it's not clear what we should do with this. Yeah, and then there is another example. You can think about one of our most studied examples in the first couple of lessons. This with the R3 with the vector product. So it's now a real Lie algebra again, even though all other Lie algebras we study now are complex. So then there is and which adjoint representation, I guess. Adjoint representation. So then there is no weight space at all, no non-zero. Weight space. Why not? Okay, for this you can just think about it geometrically, because you know this geometric interpretation of the vector product. So what would it mean to have a non-zero weight space, say a one-dimensional, or say some weight vector? So let's suppose there is a vector in R3, which is a weight vector for the adjoint representation. So let me just write it down. Suppose some vector v in R3 is a weight vector. That means for all y in R3, yx, this is what I get when I apply the adjoint action of y to x. This is why I called it v, because the x looks like the multiplication sign. So y times v is a multiple of v. But we know, right, it's also perpendicular. So if it's perpendicular, sorry. It's just a multiple and also perpendicular, then v must be 0. Right. So here the concept of weight spaces doesn't really seem to help at all. But there are also success stories. Well, most notably, several ones. So let's consider the SL2 representation Vk for k any integer, non-negative integer. I recall this was we take the homogeneous polynomials in two variables, capital X, capital Y, of degree k, and then there was some action of the Lie algebra, and so this space of homogeneous polynomials of degree k became a representation. And this was actually one of the exercises, namely 5.1. There you showed that if you take the vector space generated by a monomial, so k is the total degree, so the monomials which span this vector space vk have the form x to the I, y to the k minus I for some I. And this is a weight space, and I think you calculated the weight as being k minus 2I omega, where omega was the projection on the upper left component. But anyway, if you forgot the notation here for this exercise, it doesn't matter. So we showed that each vector space generated by a monomial is a weight space for this action. And of course, the whole thing here is just the direct sum of these vector spaces, because every homogeneous polynomial is by definition a linear combination of these monomials. So this is for all I. So in this case, Vk decomposes into weight spaces. And of course, I didn't make the most important remark here. So if you look back to this exercise, what we did is we restricted this representation to H. So this was a very important step here. So we defined this sub-algebra H of SL2C. Just consisting of the diagonal matrices. And as we're in SL2C, then also the trace must be 0, so the diagonal matrices all have the form A minus A, where A is some complex number. So we started with a representation of SL2C, Vk. Then we considered this Lie subalgebra H, just consisting of abelian matrices. And what you showed here actually is that this monomial is a weight space of this weight for all I of the restricted representation. So as a representation of the entire Lie algebra SL2, these would not be weight spaces, but if we restrict our representation just to this abelian Lie subalgebra of diagonal matrices, then these are all weight spaces, and Vk decomposes as a direct sum of weight spaces. Yeah, and there were or will be two other very similar examples.
What was W?
Excuse me?
Omega.
Omega, yeah. So this was given. So omega is a weight of the restricted representation, so it must be a linear form on H. And we know every matrix in H has the form A minus A, and omega was the linear map which just sends the matrix A minus A to A. Yeah. So anyway, but as I said, if you don't remember this, it's not so important now to recall all these definitions, but just important to note that in this special case, we have this nice property that our entire representation decomposes as a direct sum of weight spaces. So this is what I mean by a success story. So now somehow we can hope to get insight into the representation just by studying the weight spaces, because every vector is a linear combination of weight vectors. So this is good. So what was the second very similar success story? This was also one of the exercises, namely 3.3. The Lie algebra is still SL2C. And the representation is the adjoint representation restricted to H. So H is the same Lie subalgebra, just consisting of diagonal matrices. And when this was one of the first exercises to learn to work with these weight spaces and to learn the definition, then we saw that if we take the adjoint representation, so SL2 acts on SL2 by bracketing from the left and restrict it to H, then again this yields a decomposition of SL2C into weight spaces. So this was namely the weight vectors were E, F, H. I recall this was 0, 1, 0, 0. This element F was 0, 0, 1, 0. This element H was 1, 0, 0, minus 1. And we computed a lot, so we already know the weights. If we here H, E was 2E. So if I apply a multiple of H, so any element of this frac H, this Lie algebra, still E will be will be sent to a multiple of E. So the weight here is 2 omega. And here the weight is minus 2 omega, and here is H is 0, then the weight is 0. May I get some? So how comfortable are you? Maybe who is totally confused? Nobody. Who knows more or less what I'm doing here and why these twos? You? So somewhere in between. Anyway, okay, it's your responsibility to stop me. So if you're not comfortable with this, I'm willing to explain it a bit more, but otherwise I just continue. So here we have the same property. SL2C, we consider this as the vector space on which L acts, on which H acts by the adjoint representation, and we have this nice decomposition into weight spaces. And now the next, this is why you understand it, because you already worked on the next problem sheet. So for exercise 8.2c, which we'll discuss Thursday, we'll see that if we take SL3C and the adjoint representation, then there is a very similar behavior. So we study L, the SL3C, the algebra of 3 by 3 matrices with trace 0. Then we also study a subalgebra H, which is still the Lie subalgebra consisting of diagonal matrices. So this is spanned by 1, -1, 0, and 0, 1, -1. So this is just two-dimensional because we have this additional condition that the trace must be 0. And then we will see that we have the same phenomenon, that the restriction of the adjoint representation of L to H decomposes into weight spaces. Yeah. So, and this is these are our examples, and the goal is now, of course, for the next couple of lessons to understand what makes these stories so successful and to generalize this. So this is what we'll do today and next lesson. And then the entire of the rest of the seminar will be to exploit weight space decomposition. It turns out that in these situations, which we'll define now, where or which we'll find now, where we have a decomposition of the representation into weight spaces, this is an extremely powerful tool. So we will spend the rest of the semester exploiting this, and we could spend much more time on this. So, following definition. Two parts. First is we start with a semi-simple Lie algebra as usual, and X any element, and then we have this abstract Jordan decomposition, x equals d plus n. And if in this abstract Jordan decomposition n is 0, so that means x equals d, then x is called semi-simple. So this is a bit bad because now we have two meanings for the word semi-simple. For a Lie algebra, well, we know it. We've worked with this notion for Lie algebras for a long time, but now we also have a notion of semi-simplicity for an element, and this means just element x of a semi-simple Lie algebra is itself called semi-simple, the element, if the nilpotent part of the abstract Jordan decomposition vanishes, or equivalently, if x coincides with the diagonalizable part of its abstract Jordan decomposition, or let me just write down the equivalent things. Now, by the definition of the abstract Jordan decomposition, this means that the adjoint operator at x is diagonalizable. And by the last theorem, there is another equivalent condition, namely for any representation phi, any representation of our Lie algebra L, the operator phi of x is diagonalizable. These are all the equivalent statements. Yeah, maybe I should go a step back and think about, so the good situation we want to have, as in these success stories, is that we have a representation and it completely decomposes into weight spaces. That means there is a basis of our vector space which contains elements which are eigenvectors for all elements of H, of our Lie algebra with which we act. For example, E, F, and H here, this was an common eigenbasis for all elements of the Lie algebra H. E is a eigenvector of eigenvalue 2, F of minus 2, and so on. So there are two problems. If we want to find representations with many weight spaces, then we want to find representations where elements act diagonalizably. And this is why this notion of an element being semi-simple is so important. If we have a semi-simple element, then by this last theorem, this will act diagonalizably on any representation of our Lie algebra. So this is very good. So this is the first part of the definition, and then the next part is as follows. So sorry, I'm always... So in some books, Lie algebras are usually denoted with capital Roman L, and in other books and articles with a lowercase fractional g. So I'm sometimes confused. So what I want to do is, in this chapter, is from now on to switch the notation consistently to g. But whenever you see any L's around, you know that I just mixed it up, and in fact, if you want, you can choose your own convention. Always write capital L or a lowercase g. Never mind. So yeah, sorry for that. So from now on, I try always to write. There shouldn't be any capital L's anymore. Subalgebra. Well, so of course we try to imitate the situation we had here in the examples with SL n and this Lie algebra of diagonalizable of diagonal matrices. So this is as follows. H a Lie subalgebra of the semi-simple Lie algebra G is called Toral if, and there are two conditions. Any element H is semi-simple, and the second H is abelian. That means any commutators of any two elements of H vanish. So why does this seem to be a good definition? First thing is, well, I just tried to explain this. So what we will want to do is, of course, the same thing as before. In the particular examples, we will study any representations of G of the semi-simple Lie algebra, restricted to a Toral Lie algebra, and hope that the weight spaces will give a decomposition of the Lie algebra. So why could this work? First good thing is every element of our Lie algebra H is semi-simple. So each element acts diagonalizably. So for each fixed element H of our Lie subalgebra H, we find a basis of G of our representation. If we study a representation of this Lie algebra G, we find a basis on which this H acts diagonally. But it's not clear at this moment whether we find what we want to find is a basis which is an eigenbasis simultaneously for all elements of this Lie subalgebra, and this is not clear why this should exist. And the second property of H being abelian will help to ensure this. Sorry, I shouldn't talk so much, but just show the formulas. Okay, so no.
So you want every element in H to be semi-simple, and you want H to be abelian.
Yeah, that's what I want. So that's the definition. Okay, so sorry, so I did enough stupid talking for today. So now I just introduce one more convention and show a lemma. So this is a convention or something, important convention. So from now, say for the rest of the chapter, or maybe for the rest of the lecture, we fix G complex semi-simple Lie algebra. And H a Toral subalgebra. And when V is a G module, so we will study representations of our semi-simple Lie algebra. Then the notions of weight or weight vector or weight space. They will always refer to the restriction of V to H. And I don't want to always say this, so this will be implicit from now. So I consider V as an H module, if V is a G module, but with respect to weights and weight spaces, I just consider it as an H module, so as a module for the Toral subalgebra. And the next couple of times I'll say it, but eventually this will be implicit. So whenever we have a module over a semi-simple Lie algebra and talk about weights, we just mean weights for the restriction to a fixed Toral subalgebra. So this is just the situation we had encountered in the examples. And now the key lemma on which this whole theory rests is the following. So now this is just a purely linear algebra lemma. So I fix a complex finite dimensional vector space. And two matrices, or operators, from V to V. So they are supposed to be diagonalizable. Two operators from V to V. Each of them is supposed to be diagonalizable, and the they should commute. AB equals BA. And then I claim I can diagonalize them simultaneously. So there is a basis of V consisting of eigenvectors for A and B. So this is, of course, the important property. So by definition of diagonalizability, there is a basis of V consisting of eigenvectors for A, and also there is obviously a basis consisting of eigenvectors for B, but it's not clear whether there is a basis consisting of eigenvectors for both A and B simultaneously. So this is the, as I say, the key lemma on which the whole theory relies. And strangely enough, in the book, and also in the older book by Humphreys, there is no proof for this, so I just made one up. But so maybe I didn't find the most simple proof. So, but anyway, this one works. So the first step is the following. I fix a vector subspace namely the lambda eigenspace for A. Lambda is any complex number. Yeah? So I fix a complex number lambda, and then I consider the set of vectors W such that A acts on these vectors just by multiplying them with this complex number lambda. So an eigenspace for A, and I claim then W is B invariant. Yeah. What does this mean? I take any element of W, apply the matrix B, and then I still get an element of W. So how do I check this? Well, as I say, let V be any element of W. Then I apply the matrix B, and I have to check that the result is still contained in W. So I have to apply A, and I hope that this will just be lambda BV. So because multiplication by A, well, this proof will actually be shorter, so I can write it in the same line. Well, but this is what I need to show. As I suppose that they commute, I write BAV. V is an eigenvector because V was in W. So this is just B lambda V, and now lambda is just a scalar, so I can take it out. Okay, so this was the easier part. And for the step 2, it's the following. Now we know that B is diagonalizable on V. This is by assumption. And also, and now we fix W to be a B invariant subspace. So, for example, such a lambda eigenspace for A, as we proved in step 1. So let just lambda be any B invariant subspace of V. And the claim is that from these two conditions, I can conclude that the restriction of B to W, so this is an endomorphism of W, is still diagonalizable. Yeah, does anybody know how to prove this? So I think maybe if you do, it could be possible with characteristic polynomials or something. So I never heard anybody talking about this. So it's taken for granted usually, I think. But anyway, so I just finished today by giving a proof for the statement, and yeah. So how can I prove this? Let V V1 plus Vn be the decomposition of V in eigenspaces. For B, right? So we suppose that B acts diagonalizably on V, so V decomposes as a direct sum of eigenspaces, say of eigenvalue lambda I. Lambda I is the eigenvalue which B has on Vi. Now I take an element x in V. So in the larger vector space, and I decompose it according to this direct sum. Right, so I can write any element of the vector space as a sum of elements of these weight spaces. So some of these summands will be 0, some of them will be non-zero, and as I didn't fix a particular order here for the weight spaces and for the sorry if I always say weight spaces, for the eigenspaces and for the eigenvalues, I can reorder the eigenspaces, and I just suppose x1 through some xk are non-zero, and then the remaining one are 0. So then I can write down Bm of x for, well, the formula will hold for any m from 0 to infinity, but we'll only use it up to m equals k minus 1. So in particular for these m, I just write down Bmx is lambda 1 to the m x1 plus, and so on, plus lambda k to the m xk. So write down the repeated application of x by this formula. So now the crucial thing is these eigenvalues, lambda 1 to lambda k, are all different. So the van der Monde determinant is non-zero. So this is the determinant of the matrix which contains the powers of the lambda I in the rows or columns, doesn't really matter. So this is the determinant of lambda 1 to the 0 to lambda 1 to the k minus 1, and so on, lambda k to the 0 up to lambda k to the k minus 1. So, and this is, people talk much about this. This is non-zero. And so from this, I can conclude that x, bx, b squared x, and so on up to b k minus 1 x are linearly independent. So if I x1 through xk are linearly independent, and the columns of this, columns are the rows of the matrix give the coefficients of Bm of x in terms of x1 through xk. So as these coefficients, as the matrix is non-zero, has non-zero determinant, then this says that these vectors are linearly independent. And from this, I can conclude that x1 through xk are in W. Why did I start thinking about W? I think over here. No, so this element, I picked an element of W. Yeah, that's good.
I see. So the lambda is a distinct eigenvalue.
Yeah.
That's why the lambda is.
Exactly. That's good. So exactly. So I started with an element of my subspace, of my invariant subspace. So all these elements are linearly independent, and of course they are elements of W, right? Because this was an invariant subspace, and I just applied B repeatedly. And so I have a linear combination of these elements x1 through xk. And they are linearly independent, so I can just multiply the coefficients with the inverse of this Vandermonde matrix, and then I get back x1 through xk as a linear. I write x1 through xk as a linear combination of those. They're linearly independent, so this is possible. Maybe I enter an extra step here. So I can express b to the I x as a linear combination of I can express xi as a linear combination of the b to the jx. And so these x1 through xk themselves are elements of W. Right? And so W is generated by eigenvectors.